So in the last class, I introduced the James-Cummings model and showed the implications such as vacuum, Rabi oscillations, and Cummings collapse and revival when you start the system in a pure state, or if you include like a coherent state for the electromagnetic cavity mode. And so all of that, we did that in a sort of model where we are not including decay for the atom or the cavity. And then I gave you a brief overview of the physics when you do include decay. But most general form or formalism is needed to handle the case when the system is interacting with an environment. And so today I'm going to give a brief overview of the mathematical methods that are used in quantum optics for open quantum systems. Primarily there are, so once again, what do I mean by open quantum systems? At least within the sort of description that is often used in quantum optics, is that there is some system which is governed by some Hamiltonian Hs, right? Most classic example is that this is one atom, for example. Or it could also be a harmonic oscillator or a some other quantum system, mechanical oscillator, so on and so forth. But most common one is atom, superconducting qubit, NV center, especially for quantum information processing. This is what we are interested in, and this is coupled, as I was saying last time, to something that we call the reservoir, which is governed by its own Hamiltonian HR. The reservoir is sometimes often called the environment or the bath. Okay, just all they all mean the same thing in this kind of picture. And there is some coupling between this environment and the system, which is governed by the Hamiltonian HSR, right? So again, when you consider the atom, it will be typically coupled to the electromagnetic field, which has been quantized, and the coupling is typically, say, a dipole term, which goes as minus mu dot E. And you've seen examples of this when we did Wigner-Weisskopf theory, or when we did other kinds of examples with just the coupling between, like in the James-Cummings model, we took a system which was coupled just to one mode of the external electromagnetic field, but then, as I said, that electromagnetic field might itself decay into external cavity modes, and the atom can decay into all 4 pi through spontaneous emission. So the reservoir there is like two-sided. There's a reservoir for the electromagnetic field, and there's a reservoir for the atom, etc., which we can separate out. So the open part of this is that it can exchange energy via this Hamiltonian HSR, and often we don't care about what the modes of the electromagnetic of the reservoir might be. We just want to know, for example, in the end, some property of the atom. We don't want to track what is happening to the bath, the reservoir, or the environment of the system. We care more about operators that we are measuring on the atom. For example, the dipole moment, or some other observable that we care about. And so the tool that we'll often use in this description is the density matrix. Okay, so this is the density operator or density matrix. Rho, which I already introduced to you before in an earlier lecture a couple months ago, where I said that this is just sum over the all the states of the atom or of the entire system in this case. So in this case, the system has a probability PA to be in one of these states, psi A, and here by the system, I guess I should really say the whole system here, both the reservoir and the system together, we would be describing by one density operator or density matrix. So psi A is the quantum state of the system. The entire system. Okay. So, so we can imagine that even if we started the entire system in a, say, a pure state, like for the system and the reservoir together in a pure state where we just have one wave function or one state get that describes the entire system, through evolution, what will happen is that the density matrix for just the system part will no longer be in a pure state. Okay, and we saw some examples of this earlier as well. So what I'm going to do today is to show you that how do we govern or how do we write down equations for the evolution of this density matrix. Before I start, I should also say that there are sort of three main mathematical techniques that are used when we describe the evolution of these open quantum systems. The first one, which is what we'll talk about today, is called the master equation, which basically governs the evolution of this density matrix or density operator. This is, you can think of as sort of in the Schrodinger picture, right? Because we are considering the evolution of the state gets of the system, okay? The second approach, you can think of that as a sort of Heisenberg picture and gives us equations of motion for the operators. Okay, so that will give us a different way of describing the evolution of the system. But there you sort of need to know very carefully what the model for the system and the reservoir are, and the noise that is induced by the system by the reservoir or the noise operators are. But we can derive some general results from that. And then the third method, which is often used, is stochastic wave functions or Monte Carlo. Okay. Generally, that is Monte Carlo, which is useful when you do like numerical simulations of a system. Okay, so these are sort of the three categories of mathematical techniques. There are more out there, of course, but I would say these are the three broad categories of mathematical techniques that are being used for open quantum systems in quantum optics. Okay, so the properties of the density matrix, I'll just quickly recall that rho is a Hermitian matrix. So today we'll be mainly concerned with the master equation, and I'll give you some kind of flavor of what happens in the Heisenberg-Langevin equations. But as I was mentioning in the last class, I want to move on to quantum information processing in the next couple of weeks, because we have only a few weeks left, and I want to cover some of those topics. So some of this I may just give you some initial notes and ask you to do further reading, and we can explore that maybe in the presentations or something like that. Okay. So the second, that is just to like tell you like what the plan is for these for all of these three topics. Okay. So today we are just going to consider the master equation, and so the properties of the density matrix that we need to know are that it is a Hermitian matrix, Hermitian operator. The trace of the operator must be equal to 1, and that it's a positive operator, meaning that the expectation of rho in any, or I guess it's to be more specific, it's positive semi-definite, meaning that the expectation of rho in any state must be always greater than or equal to 0. Okay. Okay. So those are the properties of the operator. This should just be recalling earlier stuff. And I've already shown you in an earlier class that if you have some operator S that you want to evaluate, that is given by some summation over alpha, P alpha, psi alpha, and S psi alpha, right? That is the expectation for the operator with this, which is in some the expectation is governed by taking the expectation in each pure state psi A and then multiplying by the probability distribution to be in that particular pure state. So this is, you can immediately show, is just the trace of rho times S which is also, of course, the trace of S times rho because of the property of the trace. Okay? So, and the physical interpretation of this, we also talked about this, but I'll just remind you again. Which is that the diagonal elements of the density matrix rho give us the probability for rho to be in a particular state, right? And the off-diagonal elements represent the coherence in that density matrix or in the system, okay? And so, for example, if rho, right, which we have said, is just going to have some elements which is governed by this, right, which are expanded out in some basis n and n. So this is the representation of the density operator in one particular basis, which you can think of as just some matrix, right, which is going from rho, say, let's go, if you number them by qubit states or something, it will go from rho 0, 0 up to, say, rho 1, 1, etc. You know, you can like calculate all the different elements of this density matrix. Okay. So, as I said, for a two-level system, certainly it's just a 2 by 2 matrix. So it's just rho 0, 0, rho 1, 1, and rho 0, 1, and rho 1, 0, right? For a for 2 qubits, right, which would be a state which has, like, let's say, an entangled state, you'll get a 4 by 4 matrix, which you can calculate again by just the outer product of the column and row vectors for that particular state. So in this way, you can write down the density matrix for any given state in that form. Okay? And the diagonal elements, as I was just mentioning, represent the probability to be in that particular state, and the off-diagonal elements represent the coherence, okay? Which will tell you to what extent M and N, the two states that you're interested in, are superposed in the actual system wave function rather than just being in a classical state. So there is some phase relationship between the coefficients of M of the state where, well, the system is in state M and in state N, for example. Okay? So again, to be more specific, so the diagonal elements which are just given by this term are also, you can think of this as the expectation of the density operator, which is just which is a projector onto the system in the state M. So that's the probability to be in the state M. And rho some Mn or Nm is equal to this guy, which is now the expectation now of the state M comma n, Mn. So this is an operator which is representing this coherence. And so we know that the off-diagonal terms are the ones that we're going to care about if we want to understand that the system is truly in some kind of quantum superposition, as opposed to just being in some mixture, which, remember, a mixture is just defined as one where only the diagonal elements exist and the off-diagonal elements all go to 0. Okay? Any questions? Sorry, I thought you were saying. Okay. As an example of like why these off-diagonal elements are important, you can see that, say, rho nm plus, say, rho mn would be proportional to the expectation of the dipole moment operator. Because the dipole moment will go as, if you remember, say, is mu, the dipole moment operator will go as some mu 1, 2 times the operator 1, 2 plus mu 2, 1 times 2, 1. So you can see that the dipole moments operator will be, expectation will be governed by these off-diagonal elements in the density matrix because of that property. Okay? Okay, so that kind of quickly recalls, hopefully for you, what we talked about with density matrix before in earlier lectures. So now I also did for you, for example, what the density operator looks like in thermal. Remember when we discussed the thermal states, right, of the radiation field? What will the diagonal elements of the thermal radiation field look like is simply a distribution which is going as exponentials in the diagonals, right? So we covered that when we were talking about states of the electromagnetic field. Oh, sorry, I erased the wrong thing. But okay. Okay. Okay, so now let's talk about when you have both the system and the environment together. What will be the density matrix? Okay, so system and environment. So as I said, the system might have some states Si which govern the, let's say we are expanding the system wave function in these bases. And the reservoir might have its own set of states that govern its evolution, called that R. Okay. And the state of the universe, in this case both the system and the reservoir, right, we'll assume is actually in a pure state, which we call psi, right? So it's just one state ket that governs the state of the system and the reservoir together, and that is just given by this psi. But now let's expand this psi in terms of both the system and the reservoir. Okay, psi is some expansion of this in the complete set of basis states for both the system and the reservoir. So I just introduce that complete set over here, and I just write down the coefficients for that expansion over here. You can think of this as some Cij, some complex numbers that represent what the system is in, and this Si, Rj is just, as I told you before, is just representing the outer product of the two k's, Si and Rj for the basis states. So this is the full state of the universe, but as I said, we don't really care about what's happening to the reservoir, let's say, right, typically. Maybe the interaction between the system and the reservoir is weak. Maybe as we'll introduce these approximations, you'll see that it allows us to write some evolution purely for the system observables, okay? And let's say that this, let's say that there's a state, that there's some observable S whose expectation value that we want to calculate, then we will simply write S equals this, right? It's just the expectation of the state S in the state psi, and then okay, introduce as usual complete set of states both here and here. I introduce the complete set of states, and when I do that, I'm just going to skip those couple of mathematical steps. You get this is the sum over I, Si, and then there is S, and then you get this sum over J. Sorry, let me rewrite that over here. I have a space on the board here. So after introducing essentially the same kind of expansion of a complete set of states, I get sum over I, Si times S times sum over J Rj psi Rj over here times Si. This quantity which is in this big brackets here is what we call a partial trace, because as you can see, what it amounts to is just taking the state ket of the system and only calculating its expectation or its matrix elements with respect to the J, the Rj states of the reservoir. Okay, so if I define something that I now call the partial trace, I'll just do one quick example now, but let's just write down the definition. Rho S is called the system density matrix, is obtained by taking the trace over the reservoir observables for the density matrix of the entire universe. So that is represented by sum over all reservoir degrees of freedom, Rj, okay, times Rj rho Sr Rj. Okay, where rho Sr was the density matrix for the full system, for the full universe, and therefore the expectation of any system operator now can be written simply again as S rho S, where rho S now only involves the system of degrees of freedom, and the reservoir degrees of freedom have been traced out. So just to give a quick example, suppose you had a system psi which at the beginning, let's say the system started out in some superposition of 0 plus 1, but then the system got entangled with 1 degree of freedom, let's call it E or R, let's say. Just an example here for what I'm talking about. R0, where R0 is, say, one of the basis states for the reservoir, and let's say R1, which is orthogonal to R0 in this example, but we can make it more general if you want. So let's say that the system gets entangled with 1 degree of freedom of the reservoir, which can be in either state 0 or state 1. Okay, this is just the simplest sort of thing that you could imagine, and then. So now you can easily calculate the density matrix for the entire system. I will just skip that. We just by the same definitions that we've already talked about. You can easily show that this is just given by this matrix, right? So it's just obtained by taking the system in this. The state psi, and then writing it out as psi, where this is just say 0 R0, 0 R1, 1 R0, and 1 R1 on the representing the rows, and then similarly you have 0 R0, 0 R1. Right? So this is just the matrix, and now you can see if I take a partial trace over just those parts where the reservoir, let's say, is R0, right? Which are so for example, if I want to take a partial trace here and here, I will end up with a rho S, which is going to be completely mixed, okay? Which is just going to have the diagonal elements over here with a half outside. Okay, you can convince yourself of that because you look at, let's say, this and this, which is having the same R0 in it, so that's a half plus a 0, and then similarly the ones that have the R1 in it are similarly also going to only have the half plus a 0. So you see that we get exactly what we would have seen for the system density matrix. Looks as though it has no coherence on the off diagonal elements, even though the full system started out with the system having the in a sort of like a coherence between the R0 and R1 states here, but by tracing out the reservoir degrees of freedom, we end up with a mixed state of the system. Yes?
So, yeah, I mean, this is an easy example, so we can directly see from the density matrix.
Correct.
So what if like it's a very complicated?
Oh, of course.
Like
right.
how to calculate? I'm a little confused about the equation on the first line.
The partial trace?
Yeah. I mean, like rho SR is like from this matrix is like a 4x4 matrix.
Right.
However, the RJ, I think it's like two. It's a one. It's a Hilbert space of the two dimensions, right?
Exactly.
So in
So
that.
you'll have two components there. Say R0 rho SR R0 plus R1 rho SR R1.
Okay.
That's it.
Oh.
That's all you can calculate, right?
Yeah. But I mean, this is a dimensional mismatch.
I mean, you can literally I'm sorry?
I feel like it's kind of like dimensional mismatch because like rho SR is like 4x4.
Yes.
However, R is 1x2.
Yes.
So in this case, how do you calculate the?
I mean, if you want to calculate it here, you take wherever there's a R0 on the left hand side. Okay, maybe we should do it. Huh?
Thank you.
Right. Let's see. So we want to take only those terms which has of this type R0 rho SR R0. Okay, that's one of the first terms in this sum. Okay, so where all will we get a this? Oh, okay. If you want to do it in the let's say in the matrix representation, you can also do it that way, right? So let's take that. So R0 acting from the left is a row vector whose this is a 4x4 system, right? So it's like a 1x4 row vector here, right?
Okay.
So in this case, this will be the 1x4 row vector, which is let's see. Do it that way? Hold on a second. I see what you're saying. So now you want to do it in the matrix representation.
Yeah.
Sorry, okay, all right. I was just adding it up right here on the coefficients. So let me think how to do that in the matrix way. Okay, 1 second. All right. Because I was just adding up those terms that I know will give me the product with the 0 R0, for example, or 0 R1.
Yeah.
Let's see. Right. So I guess what you have to do is, yeah, there does seem to be a mismatch of dimension if you were to just do that. So I think you have to write down R0, even though it's, if I were to just think about R0 itself, it'll just have a 1x2 matrix.
Yes.
So if I want to write that in the matrix representation here, it seems like I have to somehow make it go into just the 1x4 type of vector. Let me think. Well, actually, I think it's all right. Let me see. In the matrix representation, you still want to end up with something that has a system degree of freedom, though, right? Because rho SR, right, was written in terms of an expansion in both Si and Rj, right?
Yes.
So it had some expansion in that. So implicitly, you know, this these Rj's, even though I write them like this, they've got to be probably written as 1 by 4 vectors. I'm not sure. Now that I think about it. Okay, I think I'll have to think about this and get back to you about the matrix representation. All right. If I were to write it in this basis, then I would just write it as wherever there is a 0 R0, I would put 1, and then I would have a 0, and then a 1, and a 0, right? That should be what R0 is in this sort of basis. And then I should have the matrix, and then I should have 1, 0, 1, 0. Let's see if that works. And I'll have to justify it more mathematically maybe next time. Why that's okay. I think it's because of this fact that they are still an outer product over here or something, right? So let's see if that works. So this is, if I take these two, that gives me a half. This gives me 0. This gives me 0. And this, did I do that right? Half goes into 0. And then this gives me half. Right? That gives me 1, 0, 1. I see. So that's only going to give me half.
Yeah. It that makes sense.
Okay. So it does make sense, but I'm not 100% convinced why I can write the reservoir degrees of freedom in this kind of representation, because of course the reservoir degrees of freedom by themselves, I think it's implicit that somehow we are also assuming that the system degrees of freedom are like, you know, being just kept as they are, so to speak.
I see.
Yeah. So that gives me one element, which is the trace over the rho 0. Or the R0, and then I have to write the one with the R1, where I'll have ones here and 1. That will be the one with the R1.
I see. Thank you.
So I think that works, but let me make sure of that. Thank you for that question. Did that make sense to everyone? At least what happens mathematically? I think that's correct, but I have to make sure that I'm not saying something that's not applicable in general. It's clearly applicable for this 2 by 2 or 2 qubit kind of system. The other way to do it is, of course, just to stare at this matrix and just add up all of the parts where the R0 is present, right? Which I think is equivalent to what I just did. So it should be okay. At least in this case, they give the same answer. Sorry, okay, so let me get back to what I was trying to say. What was I trying to say there? Yes, so we said that the state of the system is given by the partial trace, where we trace out all the environmental degrees of freedom. You can think of this also in terms of probability distributions. Like, for example, if you have two joint probabilities, of two random variables, then you can think about something which you might call a marginal probability distribution, where you just integrate out all the other probabilities for the other variable. So it's a similar idea, except it's now in the quantum kind of situation. Okay, so what is our goal? the goal of what we will do now is to find an equation of motion for rho s. So rho s, we want, this rho s, as we can see, has all the properties, can be shown to have all the properties of a density operator, but may not anymore be in a pure state, even if the universe started out in a pure state. And in particular, what we want to do is we want to solve for this rho s of t, right, or write an equation of motion for rho s of t without having to keep track of what's going on in the environment. Okay. And in general, this is not possible. Okay, so right away we can say that. Okay, it's not going to be possible to do this in the most general case. But in some relevant limits, we will be able to make an equation which we call the master equation for the evolution of this system operator. And the type of environment, therefore, because as I said, we can't do it for every type of environment. The most general equation would involve, like, any kind of environment, any kind of coupling, and that is basically impossible for us to solve, okay, or impossible for us to even calculate. Maybe we could do it with numerical methods, like I was explaining, like the Monte Carlo simulations is a common technique nowadays. But to get some analytical insight into this, we will restrict ourselves to types of environment which are very common, especially in quantum optics and quantum information type situations. Okay? So before we jump into deriving this master equation, let me talk about some relevant properties of the environment. So what I mean by this is, let's look at some simple examples of environments. And this particular model that I'm treating is sort of a very classic model for spins, which is that if you have a spin which is given by the Hamiltonian h bar omega sz, right, which is the spin operator, plus it's interacting with some random variable f of t that is, a magnetic field like acting on this same sz. So this is just an example, okay? So it will help us to get some insight into the type of environments that we're going to consider. Okay? So this is a two-level atom, and this guy f of t is random. And it's classical, okay? It's not even having any quantum state. So its average value f of t, we will choose it to be 0 just for simplicity. Okay? Of course, in the model that I was just showing you, which I erased, the system had a Hamiltonian. This is clearly the system part of the Hamiltonian, right? And then the reservoir had a Hamiltonian, right, which was the HR. But now I've done away with that because basically I said the reservoir is classical, so there is no impact of the system on the reservoir. Okay? The reservoir is completely unaffected. Think about it like, you are in the lab, you've set up a spin in your apparatus, but then there's some random electromagnetic radiation from power lines, from other radio towers and TV towers, all are going around in the lab, and they're going to act on your system. Okay? And this example is actually pretty easy to solve because the noise term is purely diagonal in SZ. Okay? So the evolution of the system from time 0 up to time t is just the exponential of this minus I omega t plus integral 0 to t f of t prime dt prime times SZ. Okay? Because the only quantum part of that commutes with itself at all times, so we have no problem in taking the exponentiation of the Schrodinger equation. Okay, so let's calculate the coherence, right? Remember, we were just talking about coherence. The coherence for the system, which is say S plus, right? S plus is nothing but this 2-1 operator for the atom, okay? Is the expectation value, okay? So when you do that, I'm going to skip some of these steps here because I want to just get to the sort of central idea here. E to the I omega t, some e to the I integral 0 to t f of t prime dt prime times s plus of 0. When I do something like this, I have to take not only a expectation of the quantum state, but I also have to consider what happens to this random variable f of t, right? Because the random variable f of t in one run of the experiment might have some time evolution, right? It's some particular realization of this f of t. But then in another run of the experiment, because I often have to repeat the experiment to obtain the expectation values, each time this f of t will have some other realization, will have some other behavior as a function of time, right? So both of those have to be taken into account. So this expectation here, maybe I should put like a double expectation, which represents both the quantum expectation value and sort of the randomization or the averaging over all the possible, sort of realizations. So sometimes you'll see it denoted by this, like a double expectation value, or sometimes you'll see it denoted by like an over bar, which represents sort of the classical expectation or the classical randomization of this classical average over all the possible realizations of this f of t. Okay? So, and this term now is going to depend, when you expand it out, right, the exponential has like 1 plus integral f of t prime dt prime plus then higher order powers. So that's going to depend on what we call the moments of the random variable, which are denoted by f of t, t1, f of t2, etc. up to f of say tn. If you expand it out to the nth term in the series of this random process, and this part, of course, is just calculating the expectation value. Okay. So let's talk about these moments of the random process, because if you're not familiar with this, it's useful to think about. This is going to be, kind of the types of noise that we're going to consider, or the types of behavior for the environment that we're going to consider. Okay. So the moments. So this is like a sort of brief sort of tour of like random variables and correlation terms. Very brief, obviously I'm not teaching a course on that, so we're just going to get some central ideas in here. So I already said that I'm going to set the average value f of t equal to 0. Okay, so that is the first moment, right? This is the first moment. Okay, and then the second moment is typically the most, the one that most people talk about, because of for certain types of processes that are very important, which are the Gaussian and random noise. Then this is the one that's most important because it governs the behavior of all the higher order moments, and this is the 2-time correlation function. Now what you'll see is when we do the evolution of the entire system, going back to the quantum situation, when we look at the behavior of the density matrix as a function of time, we will observe that there will be 2-time correlation functions which will be evaluated with the environment operators. So this will be a generalization of the 2-time correlation function, but going into the quantum regime for like the reservoir operators. Okay. But in some sense, it's a very similar idea as this two-time correlation function for the classical situation. Okay. So at time t equal to t prime, this, so if I set t equal to t prime there, I get the average of f of t squared, right? Which is like the variance of the random variable f of t. So yeah, so like, when you think about it, right, the typical random variable, let's say temperature of this room or the weather outside, like that's like classic random variables that you can think about. Then we think about like, okay, let's say on average the temperature just stays at say 70 degrees or something like that inside this room, but there will be some fluctuations around that point, okay? And of course we can estimate sort of the size of those fluctuations by calculating the variance of the temperature at different times, okay? Then we can also ask, if I know the temperature at one time, what is the probability or what is the idea how much will be the temperature be at some other time later? And we know like within an hour or so the temperature in this room is probably not going to change so much, okay? I mean, of course with all the air conditioning and stuff, it probably stays pretty constant, close to 70 degrees. So maybe a better example is the weather outside, which is more subjected to random fluctuations. And we know, so let's say the temperature is 55, it's going to be around 55, an hour from now, 2 hours from now, but maybe within about like a day, we know that the temperature might no longer be close to 55, right? So this is the idea of the correlation time. In this case, we can say the correlation time for the weather outside, the temperature outside, is roughly on the order of a day, right? In the same way, we can ask like what are the correlations or similarly the correlation times for like other kinds of random noise that your system is subjected to. And so one of the properties, of course, is just simply the variance. This just tells you like the size of the fluctuations. So that is just sigma f squared of t, which is equal to the variance of this random variable. And this will be usually greater than 0, right? It's defined to be greater than 0 there. So the thing that we're going to assume is that this will be independent of time. So the size of the fluctuations is independent of time, which is often called a stationary process. Because it doesn't depend at what time you're going to observe this size fluctuation. And this is averaged, of course, over all the possible realizations of this f of t. So, sorry. If I want to use, say, overbar for like classical averaging or randomization, and I reserve the angle brackets for the quantum expectation value. Okay. And so, for a stationary process, this f of t prime over bar is simply equal to f of t minus t prime times f of 0. So it does not depend on the time t and t prime individually, but only on the difference between them. Okay, that's what a stationary process is, and typically it is going to fall off as this difference in time tau increases. Okay, this is tau, which represents the difference in the time, and we can define some correlation, which I was just giving you that sort of general intuition that there is some time scale over which we can predict what happens to the function, and then after that time it disappears. And so, for example, the simplest model for this correlation time will be that f of tau, f of 0, this over bar, is say a constant for tau lesser than tau c, and then equal to 0 for tau greater than tau c. Right? This would be a simplest sort of model for the correlation function. Okay. Of course, you can ask, what about the higher order moments, right? We haven't evaluated those. Well, for a very specific case, which is very commonly assumed in many systems, if we assume that this noise is randomly distributed by a Gaussian distribution, then you can show that all of the higher order moments can be expressed in terms of the first moment and the second moment. Okay, I'm not proving these results, but they're not too hard to understand because we can show that all the higher order moments factorize into these products of f of t and f of t prime. Okay? And so if you assume Gaussian distributed random variables, then all the higher order moments are determined. And in particular, what is interesting, remember that we had this result, which I have now erased, which is the expectation of this, remember we had this S plus, right? I'll just rewrite it again, is equal to e to the I, there was an e to the I omega t, it's not so important, but then there was an e to the I f of t prime dt prime from 0 up to t of S plus of 0. Okay? And when I take this average, as I was saying, we are going to have to calculate those higher order moments, but the sum of, so basically what we have here in this phase is a sum of many different random variables, right, because it's an integral over a random process, that's equivalent to the sum over many different random variables, each of which is Gaussian distributed. Therefore, we can write the sum also as a Gaussian distribution, and therefore all what we're going to show, or it can be shown, again I'm just going to, is equal to say e to the I omega t, let's say e to the I chi of t times some S plus of 0. Okay? Trace of this. Trace of S plus times. That's the quantum expectation value. And so what is this? The reason I go into some detail with this particular classical noise model is because it's very helpful when one thinks about experiments involving spin echo and so on, when you're doing quantum information processing and you're trying to decouple the spin from the environment. So I'll just solve for this e to the I chi, where the chi is just this integral over this f of t prime. So integral, so this expectation value now I'm going to assume it's Gaussian distributed, because I'm saying that without proof, but the sum of all these Gaussian variables is going to be another Gaussian variable. So it's just e to the minus chi squared over 2, some, where sigma t is some variance of this chi, e to the I chi, d chi, right? That's the expectation for e to the I chi. Okay, and that you can easily show is just e to the minus sigma t squared over 2. Okay, where sigma t squared is equal to expectation of chi of t squared, or the variance of this chi of t squared. Okay. Okay, you can carry out more of this. But you notice that the important thing is that we have gone from something that looked like e to the I chi to something that looks like an exponential decay with this sigma t squared. And you can evaluate the sigma t squared for different variances. And in fact, in the homework, I'll show you one or two of these. I'll assign you like a particular model for these different cases, but we can already see some simple, properties of this decay. So I'll give you like a very specific process which has a certain random distribution, and then you have to evaluate, let's say, some of these integrals, and you can actually calculate the decay of the coherence for different situations. Okay, so let's just look at some limits first. Okay. So in the first limit, I take t far lesser than tau c. Okay. So when we have that this f of t is pretty much for t much lesser than the correlation time, remember the model was we're going to have f of t is just a constant. Okay. So we just have to average over all the possible values of f. Let's say that value is just some constant, f of t is equal to some constant f for t far lesser than tau c. Then the chi, that integral, right, if f of t is constant, is just going to be linearly dependent on time plus this f times t. Okay? So, which implies that sigma t squared is just going to be some variance of this f times t squared. Okay? And so that means that the exponential over here goes as e to the minus f squared times t squared divided by 2. So that's like a decay which goes as this Gaussian decay. Okay, so this is the coherence, remember? So this was the expectation of S plus. Okay. So for short times where f of t is constant, there is a decay which is going as this Gaussian decay. Okay, so if you think about experiments with nuclear magnetic resonance or a spin that is subjected to some classical random noise, which is constant with time for some correlation time, right? Then you should expect to see a Gaussian decay. And in fact, in many nuclear magnetic resonance experiments, experiments where the coherence time of the environment or the memory time of the environment is very long, it essentially means that the environment remains sort of constant. For example, you might have an electron spin that's interacting with a bunch of nuclear spins, and the nuclear spins are very weakly interacting with each other. Okay? So because they're weakly interacting with each other, you can think of them as creating some random noise field on the electron spin with some very long memory time, because the nuclear spins are sort of frozen in some initial state and they just don't really cause much of like a change, or they don't like really talk to each other, so they have a long memory of whatever the system started out with. Okay, so in this situation, then you should expect to see some kind of Gaussian decay of the coherence. But also, there's another interesting point of this. If f of t is truly constant over some time scale t, you might ask yourself, then isn't that just like I can reverse some of the dynamics and recover back the original value that I started with? And this is the idea of the spin echo. Basically what you do is you start the system in a coherent time, in a coherent state. So if you go back, let's say to the block vector picture, right, for a single spin. So you started the system initially in the ground state. Let's say that the block vector was pointing down on the block sphere, and then you create some coherence by carrying out a pi over 2 pulse, like we have seen before, right? So now the system is, let's say, in the x state, okay? And so let me just look from the top. This is the system starts out in the x state, right? And remember, the model of this Hamiltonian is that there is just a perturbation, a random noise along the z direction, right? That was the model. There's some classical random noise that's acting along the z direction. And for time tau lesser than tau c, that's a constant. So in one realization of the experiment, your spin vector will precess around this constant magnetic field and will accumulate some phi 1. Okay. In the next realization, you'll get some phi 2, phi 3, etc. So you'll get some spread in these vectors over time, and what I've shown is that in fact this spread will grow, will decay according to the Gaussian dependence of the time scale. Okay, so that's what we have just shown. But what Hahn realized was that if I don't just apply just the 1 pi over 2 pulse, but after some time t, I apply another pi pulse around, let's say, the same axis, or let's say around this axis, for example, then I've inverted sort of the behavior. So like now, after some time phi 1, let's say the first time it went over some time scale, so now the pulse sequence is, I have a pi over 2 pulse, I wait some time tau, and then I apply a pi pulse. Okay? So initially, the spin vector had accumulated some phase phi, and now because I have applied the pi pulse, I have rotated the spin vector around, let's say, the x-axis or the y-axis. It doesn't really matter too much. Let's say you applied it around the x-axis, you flip the spin over to this side. And now remember, it's again evolving under the same action of the same variable, the magnetic field, which is remaining constant over the time scale t, which is much lesser than tau c, or let's call this t, sorry, not tau. So t is much lesser than tau c, so which means that it will accumulate the same phase again. And it will recover back to the original state. And so this is why when a Hahn echo system will work, as long as the system is in, or the environment has some memory, as I like to call it, of the original state of this system, okay, or of the environment doesn't change too fast, basically. That's what it means. But that too fast can depend on the time scales of evolution of the environment and the system itself, the spin in this case. So if you can like quickly average out these behavior of this environment, as long as the environment has some memory, because this coherence time of this, or correlation time of the environment is long compared to the evolution time of your system, you can always echo out, as we like to call it, or spin echo the environment and recover back the original dynamics of the system. But that depends on this sort of this parameter t being much lesser than the correlation time of the environment. Okay? So that is the first sort of interesting thing we have now learned. In the other limit, when t is much greater than tau c, okay? So this limit, which is when you can do spin echo, is called the quasi-static limit sometimes, because the environment has basically remained almost in a constant state during the evolution. And that's also beyond just that, you can derive for like different types of environments, like what the decay might look like. All you need to know is sort of like the behavior of the random variable f of t. But now let's take the other example. So t far greater than tau c. In this situation, basically f of t becomes completely uncorrelated with itself within some time. And let's say, like for example, it's instantaneous. Like so we call this the Markovian environment, which is, say, it has some delta function like behavior. So now, no matter what the time scale I choose, the environment does not remember its state from the previous moment in time. It only knows its memory, or retains its memory for a very short instant of time. So that is the t far greater than tau c situation. Then you can evaluate again the sigma t squared chi of t whole squared is I keep forgetting. I wanted to maintain the overbar for the random variable. Was I careful about that here? Oh, I wasn't. Sorry. So this is classical randomization, and then of course there's a quantum part, which is the expectation value. Okay. Okay. So again, I calculate out those integrals, double prime, t prime and dt double prime, f of t double prime, f of t prime, average. So I put back the delta function, and that's just going to give me integral 0 to t of gamma dt prime, right? I just calculated the expectation for this. I put back this expectation for this 2-time correlation function, which is gamma times t. So in this case, we had the decay going as an exponential, as a Gaussian decay. In this case, we are going to have the coherence going now as e to the minus gamma t over 2. Okay? So it's a single exponential. So it's very qualitatively different. And so this is another statement you'll often see when people are doing these kind of resonance experiments, spin qubits, maybe superconducting qubits, etc. That initially they may observe a Gaussian decay, and eventually they expect it to roll off into an exponential decay. Okay, and often the exponential decay means you can no longer remember. In this situation, the time scale is much greater than the correlation time of the environment, which means you have no memory of what happened in earlier times, and that means techniques like spin echo can no longer work for you. Okay. Then the only way to improve is by somehow reducing sort of the strength of the noise. So you have to do better job of making your qubit shielded from the environment that it is in. Okay? This is called the Markovian environment. Markovian. Because as I said, the system or the environment no longer remembers what happened in an earlier instant of time. Okay. So now, what we're going to do, so even if you don't remember all the mathematics later, I think the important thing to take away is that there are typically these two regimes of evolution for the spin qubit that's coupled to a classical random variable. One is the t far lesser than the correlation time, when we expect the sort of a Gaussian decay, and for t much greater than tau c, you get this sort of exponential decay. In this case, when it's in this sort of behaving like this Gaussian decay, or when the system has a memory of earlier times, okay, and as I gave you that sort of example in the back of your mind, it is spin interacting with, say, some weak nuclear spins or something that have a long memory time, then you can always use spin echo to recover the original coherence, so you don't have to necessarily lose the information that you stored in the coherence. And so this is a very common technique in many situations in quantum information processing, that will periodically apply a pi pulse to recover the original memory of the system. In fact, as you can see, you can keep putting more and more pi pulses, and you can keep recovering the state of the original system as long as the environment retains its memory of that particular initial starting point. And this other regime, t far greater than tau c, you have gone into what we call the Markovian regime, where the system you cannot recover anymore, and it's just going to decay exponentially with time, linearly exponentially with time. Here it is a Gaussian decay. Okay, so what I want to say here is that this Markovian environment is actually a very, very important environment, because the electromagnetic field, as you'll see when we evaluate. So remember now, I had to evaluate these two-time correlation functions, f of t prime. Here I assume these were classical variables, right? Just some external power line or electromagnetic waves coming in from the TV and radio towers and so on. But what if these are quantum systems? Okay, and in particular, if you have an electromagnetic field which has an infinite number of degrees of freedom, then we will show that this correlation function for the environment, the electromagnetic field, now evaluated in a quantum way. Right now, we have to also take the trace of the environment degrees of freedom in this two-time correlation function and evaluate it. So we'll have to take an expectation using the density matrix of the system and the reservoir, and you can calculate just the trace over the reservoir variables, replace these by the quantum versions of the operators that couple the system to the environment. So you replace this by operators and then calculate the expectation value, and then you'll show that that will also behave like this kind of delta of t minus t prime, that gives us the Markovian behavior. And since this is such an important reservoir for many systems, where atom or superconducting qubit or NV center, etc., are interacting with the external electromagnetic field modes, we will now consider the quantum treatment of this particular system. And I'm going to give you the notes for this and lead you through sort of the basic approximations, and you can follow the details of the math in the notes. So let me just set up the problem, and then we will come back to it, or I'll give you the notes for the. I'll just tell you about the main approximations for this system. Okay. So the treatment now. The reason we are considering this is because of this earlier discussion. So system which is bilinearly coupled. I'll explain what that means in a second. To Markovian reservoir. Okay. Once again, the universe is governed by this Hamiltonian, Hs plus Hr plus Hsr. Okay. The first two are completely uninteresting to us. We are just not going to worry about that. That's the system and the reservoir on its own. The one we really care about is Hsr, right? And what I'm going to treat is that bilinear coupling, which is that S and R are coupled in this way. Okay? This is the bilinear coupling that I'm talking about. Okay? The S operators act only on the system degree of freedom. The R operators act only on the reservoir degrees of freedom. And the classic example of this example is atom interacting with electromagnetic field. Because as I showed you in earlier lectures, for example, when we did Wigner-Weisskopf theory, that the system and reservoir coupling is just minus H bar Gj Aj to 1 plus Hermitian conjugate, right? So when you are going from the state 1 of the atom to the state 2, you have to destroy a photon from the electromagnetic field and vice versa. So here you can clearly see this is the reservoir Hamiltonian reservoir operators, and this would be the system operator S dagger and vice versa. Okay. So as you can see then, when we start evaluating the evolution of the density matrix, we'll come across terms that involve the system and the reservoir wave function, the reservoir operators, and we are going to have to evaluate that reservoir operator in these two-time correlation functions. Okay, I guess I'll stop there for today. We did start a little bit late, but the rest of this is basically talking about the approximations that we'll make to solve this problem and get the result, which is the master equation. Okay, any questions about this part? And I still have to answer your question on. I think what I said was right, but I will make sure of that and get back to you next time. Yeah. Any other questions? Okay, all right, thanks.